Cryptocurrency nodes are computers that run software to validate and relay transactions on a blockchain network. They form the backbone of decentralized cryptocurrency systems by maintaining a copy of the blockchain and enforcing the network's rules. Each node maintains a copy of the blockchain, which is a chain of blocks containing transaction data. Nodes ensure that all transactions follow the protocol rules and reject invalid transactions. This creates a trustless system where no central authority is needed to verify transactions. Key properties of cryptocurrency nodes include transaction validation, consensus enforcement, and maintaining network security. The decentralized nature of nodes provides resistance against censorship, eliminates single points of failure, and ensures global accessibility. Cryptocurrency nodes work together to create a secure, transparent financial ecosystem that operates without centralized control. Cryptocurrency networks rely on different types of nodes, each playing a specific role in maintaining the network. Full nodes maintain a complete copy of the blockchain. They independently validate all transactions and blocks, ensuring they comply with consensus rules. Full nodes are crucial for enforcing network rules and providing the security backbone of cryptocurrency networks. They require significant storage capacity but offer complete autonomy. Light nodes, also known as SPV or simplified payment verification nodes, only store block headers rather than the entire blockchain. They rely on full nodes for transaction verification, making them suitable for devices with limited resources like smartphones and IoT devices. Light nodes provide a good balance between security and efficiency. Mining nodes are specialized nodes in proof-of-work networks like Bitcoin. They perform all the functions of full nodes, validating transactions and maintaining the blockchain. What makes mining nodes unique is their role in competing to solve cryptographic puzzles to create new blocks. Successful miners earn block rewards and transaction fees as incentives. Masternodes are special nodes found in certain cryptocurrencies like Dash and PIVX. They perform specialized functions beyond the capabilities of regular nodes. These functions often include enabling private or instant transactions, participating in governance voting, and supporting other advanced features. Unlike regular nodes, masternodes typically require operators to lock up a significant amount of cryptocurrency as collateral. Full nodes form the backbone of cryptocurrency networks by downloading and verifying every block and transaction against the network's consensus rules. Unlike light nodes that rely on other sources for verification, full nodes independently validate everything themselves, making them critical for maintaining the network's integrity. When a new transaction is broadcast to the network, full nodes begin a thorough validation process. First, they verify that the sender has sufficient funds by checking their wallet balance in the blockchain history. Next, they validate the transaction's cryptographic signature to ensure it was actually created by the owner of the sending address. They also check that the transaction follows the correct format according to the network's protocol rules. If the transaction passes all validation checks, the full node will propagate it to other nodes in the network. Full nodes also validate new blocks added to the blockchain. When miners or validators create a new block, full nodes verify it before accepting it into their local copy of the blockchain. First, they verify every transaction contained within the block, ensuring each one is valid according to the network's rules. They check that the block itself follows all consensus rules, including correct formatting, valid references to previous blocks, and proper timestamp. Full nodes verify the proof-of-work solution in the case of Bitcoin, or the validator signatures in proof-of-stake networks like Ethereum. If the block passes all validation checks, the full node adds it to its local copy of the blockchain. This comprehensive verification process makes full nodes crucial for the security and integrity of cryptocurrency networks. By independently verifying every transaction and block, full nodes prevent double spending attacks and ensure consistent enforcement of consensus rules. Their distributed nature creates network resilience through decentralization, and they maintain the historical accuracy of the entire blockchain. Light nodes play a crucial role in cryptocurrency networks, offering a resource-efficient alternative to full nodes. Also known as SPV, or Simplified Payment Verification nodes, they provide a more accessible way to interact with blockchain networks. Unlike full nodes that store the entire blockchain, light nodes download only block headers, dramatically reducing resource requirements. This makes them ideal for mobile devices and computers with limited storage and processing power. Light nodes verify transactions using Merkle proofs, an efficient cryptographic method. This allows them to confirm if a transaction is included in a block without downloading the entire block's data. While less secure than full nodes, light nodes make a reasonable trade-off between security and accessibility. By requiring fewer resources, light nodes lower the barrier to entry and allow more users to participate in cryptocurrency networks. In summary, light nodes are essential components of cryptocurrency ecosystems, striking a balance between resource efficiency and security while making blockchain technology more accessible. Mining nodes perform the critical function of adding new blocks to the blockchain in proof-of-work cryptocurrencies like Bitcoin. These specialized nodes compete to validate transactions and create new blocks, which are then added to the chain. Mining nodes first collect pending transactions from the network's memory pool or mempool. Each mining node verifies these transactions to ensure they are valid according to the network's rules. After collecting and verifying transactions, miners compete to solve a cryptographic puzzle, a process known as mining. This puzzle involves finding a special number called a nonce that, when combined with the block's data and hashed, produces a result below a specific target. The first miner to solve the puzzle gets to create a new block and add it to the blockchain. This block is then broadcast to the network and, once verified by other nodes, becomes a permanent part of the blockchain. As a reward for their computational work, miners receive newly minted coins, currently 6.25 bitcoins per block, plus the transaction fees from all transactions included in their block. Mining requires specialized hardware such as application-specific integrated circuits, ASICs for Bitcoin, or graphics processing units, GPUs, for some other cryptocurrencies. These mining operations consume significant amounts of electricity, as the computational work is extremely intensive and runs continuously. Despite the resource-intensive nature of mining, these nodes play a critical role in securing the network and maintaining the integrity of the blockchain. In proof-of-stake cryptocurrencies, validator nodes have replaced the energy-intensive miners found in proof-of-work systems. Unlike miners who compete by solving complex puzzles, validator nodes are selected to create new blocks based on the amount of cryptocurrency they've staked as collateral. Staking involves validators locking up their cryptocurrency as collateral. The more they stake, the higher their chances of being selected to validate transactions and create new blocks. This probabilistic selection process is proportional to the amount staked, ensuring those with more at stake have more influence in the network. Validators perform three key functions. They verify transactions, propose new blocks to the blockchain, and attest to blocks proposed by other validators. A key advantage of proof-of-stake is its energy efficiency. While proof-of-work networks like Bitcoin consume massive amounts of electricity, proof-of-stake networks like Ethereum 2.0 use approximately 99% less energy. Validators are incentivized through staking rewards, earning returns proportional to their stake for helping secure the network. Annual yields typically range from 4 to 15%, depending on the specific cryptocurrency and network conditions. As proof-of-stake networks continue to evolve, validator nodes will play an increasingly important role in securing and maintaining blockchain ecosystems. Node decentralization is the foundation of cryptocurrency security. A decentralized network consists of many independent nodes distributed across the network, each maintaining a copy of the blockchain. Geographic distribution of nodes is crucial for network resilience. When nodes are spread across different regions, the network can withstand localized disruptions, regulatory actions, or infrastructure failures. To understand the security benefits of decentralization, Let's compare centralized and decentralized networks. In a centralized network, a single entity controls the entire system, creating a single point of failure. Decentralized networks distribute control among many participants. One of the key security properties of decentralized networks is attack resistance. When a large number of independent nodes validate transactions and blocks, it becomes extremely difficult for any attacker to compromise the network. An attack would require controlling more than 50% of all nodes, which becomes increasingly difficult as the network grows. Running a node contributes to the cryptocurrency ecosystem in multiple ways, even without direct financial rewards. Nodes enhance network security by validating transactions and blocks. They increase censorship resistance by ensuring transactions can't be easily blocked. They verify the blockchain independently, propagate transactions, and improve overall network resilience. Setting up and running a cryptocurrency node requires several steps and considerations to ensure proper network participation. The setup process involves four main steps. First, download the official node software for your chosen cryptocurrency. Popular choices include Bitcoin Core for Bitcoin and Geth for Ethereum. Second, install and configure the software. This includes setting up the data directory, configuring network settings, and implementing security measures. Third, synchronize the blockchain. This involves downloading and verifying the entire transaction history, which can take several days depending on the cryptocurrency. Finally, connect to the network by establishing peer connections. This may require port forwarding and firewall configuration to ensure optimal connectivity. Hardware requirements vary significantly between different cryptocurrencies. Let's compare the requirements for Bitcoin and Ethereum nodes. Bitcoin full nodes require around 500 gigabytes of storage, a 1 gigahertz processor, and at least 2 gigabytes of RAM. Ethereum nodes are more resource-intensive, needing over 1 terabyte of storage, a quad-core processor, and at least 8 gigabytes of RAM due to the additional complexity of storing the state database. There are two main options for hosting a cryptocurrency node: home setup or cloud hosting. A home setup gives you complete control over your node and contributes more to network decentralization. However, it comes with higher electricity costs and requires regular technical maintenance. Cloud hosting offers lower upfront investment and reliable uptime, but it typically involves monthly subscription costs and provides less control while contributing less to network decentralization. Node maintenance is a critical ongoing process that follows a continuous cycle. Regular maintenance includes keeping software updated to ensure compatibility with the network. Security patches should be applied promptly to protect against vulnerabilities. You must also prepare for protocol upgrades, also known as hard forks, which may require significant changes to your node configuration. Finally, regular monitoring of system performance and available disk space is essential for long-term operation. By properly setting up and maintaining your node, you become an active participant in the cryptocurrency network, contributing to its security, decentralization, and overall health. Different types of cryptocurrency nodes have varying economic incentives, creating a diverse ecosystem of operators. Mining nodes receive direct rewards in the form of newly minted coins and transaction fees. They compete through computational work in a process requiring significant hardware investment. Similarly, validator nodes in proof-of-stake networks earn staking rewards and transaction fees. However, they risk having their staked coins slashed if they misbehave. Masternode operators typically receive a portion of block rewards for providing special services like instant or private transactions. These nodes require significant coin collateral as stake. Regular full nodes generally don't receive direct monetary compensation. They operate instead for ideological reasons, to support the network, or to gain benefits like enhanced privacy, trustless verification, and faster transaction broadcasts. The ecosystem is evolving with projects like Pocket Network and Flux, creating new incentive structures for running regular nodes. These models reward operators for providing specific services to the network. These varied economic incentives ensure network participation, driving both security and decentralization of cryptocurrency networks. Node technology in cryptocurrencies is rapidly evolving to address the fundamental challenges of scalability and accessibility. Light client protocols are being developed that maintain robust security while requiring minimal computational resources and storage. These protocols verify blockchain data using cryptographic proofs rather than processing entire blocks. Sharding is another promising innovation that divides the blockchain into smaller, manageable segments called shards. Each shard processes its own transactions and stores its own data, allowing the network to process multiple transactions simultaneously and significantly increasing throughput. Zero-knowledge proofs allow nodes to verify the validity of transactions without processing all the underlying data. This technology can dramatically reduce the computational burden on nodes while maintaining the same level of security, enabling more efficient validation processes. Node as a service providers are making it significantly easier for developers to access blockchain networks without running their own infrastructure. These services manage the technical complexities of maintaining nodes, allowing developers to focus on building applications. As cryptocurrencies mature, a key challenge remains: maintaining sufficient decentralization of nodes while improving performance. More efficient nodes could lead to fewer operators, potentially compromising the network's censorship resistance and security. The future of cryptocurrency nodes lies in finding the right balance between technological innovation and maintaining the core principles of decentralization. As these technologies mature, we can expect more efficient, accessible, and powerful node infrastructure that supports the continued growth of blockchain networks.